So last time, before the break, we covered section 6.1, which was discrete probability distributions, where you can make a table and you can list all the possible values that x can take on, and then the probability of each of those values of x. Okay? So today, section 6.2 is continuous probability distributions. And continuous probability distributions are similar to what we did with discrete, but the random variable x is continuous. So x is a random variable, but it can take on either a large number of possible values or theoretically an infinite number of possible values. Now, the way we measure things, it can never actually be infinite, but you can think of it that way. To start this discussion with continuous probability distributions, actually at the end of section 6.1, the author talks about the uniform probability distribution. So we let x equal a random number between 0 and 1. So in that interval. Right? How many numbers are in that interval?
You mean those two or between those two?
Between those.
Infinite.
In this interval. If x can be a continuous number in between those, between 0 and 1, there's an infinite number of possible values, right? So what's the probability that, let's say, what's the probability that x is equal to 0.5? If I have my random variable be any number between here, and we're going to call it a uniform distribution. So all values are equally likely. If all values in between 0 and 1 are equally likely to occur, I guess before I go any further, let me pull up the TI-84, and you can get your calculators out. Let me dim the lights. So you can see in TI-84 here, and if you click on the math button, so I clicked on the math button and I get this menu, math, num, CX, CPX, and PRB. Go over to PRB. And that's short for probability. Then we've been here before and we've done the rand int. Well, that's a uniform random integer between whatever numbers you tell it. And I think we did between 1 and 25 or whatever. Uniform means that all the numbers in there are equally likely to be chosen. Well, the first one that's highlighted by default is rand, the word rand, which is short for random. And if you press enter on rand, you get the word rand in your screen and a blinking cursor. There's no parentheses or anything, so just press enter. And what you should get is a number that's in this interval. It's bigger than 0, but it's less than 1. Alright? Anybody get the same number I got? I got 0.85309. No? Okay, good. Remember, when the calculator first comes from the factory, sometimes they're set with a random number seed. What number did you get?
0.5973.
0.5973. Anybody else get that same number? Okay. I think I didn't know if maybe each of the random number generators you have to get out of sync, or just once you do one of them, then the rest of them are all out of sync. That must be the case. If nobody's getting the same number, then we're good to go. Okay? And if you just press enter again, it'll give you another one. So there's 3 random numbers. So what's the probability that x is equal to 0.5? When you hit enter, what's the probability that you get 0.5? 1 out of infinite. That ain't a very big number. In fact, 1 over infinity, you can't even compute that, right? But you can if you've had any calculus, or think about, well, make the bottom of a fraction bigger and bigger and bigger. Because even in the calculator, it isn't truly infinite. It's keeping 10 decimal places. Which 10 decimal places, let's see, a million has 6 zeros. So 10 million has 7, 100 million 8, a billion has 9. So we got the 10 billion possible numbers here in your calculator. 10 billion. So the probability it comes up 0.5 is 1 out of 10 billion. Yeah, that's pretty much infinity. Well, 1 over 10 billion is pretty much what? Pretty much nothing. Pretty much 0, right? 1 over a huge number is very, very close to 0. So the probability in a continuous distribution, the probability of getting exactly one number is 0. Yet, when you take all the numbers together, the total probability is 1. Well, that just doesn't seem to make sense. Your mind really can't handle that. Well, I got an infinite number of values that all have probability of 0, but yet, when I sum them up, I get a probability of 1. But it's a calculus thing. What would this distribution look like if I graphed it? Well, think about graphs of distributions. Last time we did discrete distributions, and we drew a bar graph. And we had height of the bar equal to the probability of that value. Well, I can't do that here because every value has probability 0. So the height would be 0. But I've got to work it out so that the probability in any region is equal to the probability of getting a number in that region. Right? Well, how much total probability is there? Right. So think of it this way. What's the probability that I hit enter and I get a number between 0 and 1? Probability is 1. Right? I'm going to get a number between 0 and 1. So what I need is, remember we talked about the area under a probability distribution curve gives you the probability of being in a region. Like we did normal distribution, normal curve, and we used the empirical rule. And we said in between plus and minus 1 standard deviation was 0.68. So that's the area under the curve in there. Well, what's this uniform distribution going to look like? How would I draw that? It's not a trick question. This one is a bell-shaped curve. The taller the curve is, the more likely those values are, right? A uniform distribution should look like what then? A horizontal line. Good. So it's going to look like that. And it's going to drop off to 0 for numbers less than 0 or numbers bigger than 1, because they're not possible. They have probability 0. Now, how tall is this thing right there? No. This makes it look like it ought to be 0, but it's not. I have to have an area of what? 1. Total probability. So how tall does it have to be so that the area of that rectangle is 1? 1. It has to be at 1. Right? So now we can't talk about the probability that x is equal to something. All we can talk about is the probability that x is in some range, like between 0.2 and 0.3. Oops, I forgot my less than symbol. What's the probability that x is in between 0.2 and 0.3? Well, if I come over here to my picture, there's point, that's not about right. It'd be about right there and about right there. So 0.2, 0.3. I'm going to shade under the probability distribution the region that I want the probability of. And the area under a continuous distribution gives you the probability for that region. So what is this answer? What's the area of that rectangle I just shaded? 0.1. It has a width of 0.1 and a height of 1. And it's a rectangle shape. So that probability is 0.1. What's the probability of getting a random number that is less than 0.25? Probability that x is less than 0.25. 0.25. Why is it 0.25? Well, you can do it by drawing it, figuring the area of a rectangle. So there's 0.25. Okay, well, that's a fourth of the possible numbers, right? So you can think of it that way. Of the interval 0 to 1, numbers less than 0.25, well, that's 1/4 of that interval, so the probability ought to be 0.25. Now, look at your calculator on the first one that you generated. How many people got a number less than 0.25? I did not. How many people did? 1, 2, anybody else? So 2 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and I'm 19. I wish we had 20 because then 25% would be easy. But 2 out of 19 people. Give me that as a decimal. Point what?
105.
Point
105.
1053. Okay. So in this class we got about 11%, but theoretically there's a 25% chance you could. Right? Why are we off by so much? Small sample. If we kept repeating it and had each of you generate 100 numbers, then we'd have 1,900 numbers to look at, and we could count how many of those actually fell, and it'd be pretty close to 0.25. Okay? Did you start to ask a question? Somebody? You? Okay.
The first number I had only had 9 decimal places. Is that normal?
The first one you did had
The
9?
first one I did had 9. The second two I
That just
had
means
10.
the last number's
Yeah, that means the last number happened to have been a 0, so then it doesn't print it. But it's kind of unusual. But, well, I guess there's a 1 in 10 chance that that digit would be a 0. We're into probability, right? Okay? So that's a continuous probability distribution. The main point of all this, you will have a homework problem on the online homework that is a uniform distribution, and they ask you to compute the probability of some region. And every time you work the problem, you'll get a different region. But it's just figure the distance, the width of the rectangle, multiply by 1, and you got it. Okay? Now, what about normal distributions? That's really the important continuous distribution that we'll work with this semester is a bell-shaped curve. So let's talk about pulses. Right? Pulse is not truly a continuous random variable, but it has enough possible values that we can treat it as continuous. And we can draw a histogram and then kind of smooth that histogram out. So the pulse distribution was pretty bell-shaped and symmetric, and it had a center of around 72 beats a minute. It wasn't exactly 72, but it was close to that. And the standard deviation, you remember what it was close to? Close to 12? Yeah, that rings a bell. I was going to say 11 or 12, somewhere in there. So if I go halfway down the hill, how far should I be out? This distance would be how far? 12. 1 standard deviation. So 1 standard deviation out, 72 plus 12 would be 84. Right? 72 minus 12 would be 60. Okay? From a continuous distribution, You cannot calculate the probabilities of a single number. Like, what's the probability that a randomly selected person is exactly 72? That number would be 0 if it were truly a continuous random variable. But we talk about intervals. So what's the probability that a randomly selected person is between 60 and 84? 68%. And I know what you're thinking. Man, we've already done this. Yeah, we have. That's called the empirical rule, because I just happened to give you two numbers that were perfect integer multiples of number of standard deviations. Right? So then you can use the empirical rule. But what about this? Between 64 and 94. That one you can't do using the empirical rule because it's not integer multiples away from the mean. So let's start with that concept of multiple integers of the mean, multiple integers of the standard deviation. If I have well, let me do it this way. I'm going to write several things down. This time I didn't tell you what the mean was. I didn't tell you what the standard deviation was. I just used their parameter symbols, mu and sigma. But what is this probability? The mean minus 1 standard deviation up to the mean plus 1 standard deviation. That's this, isn't it? That's this case. So this is 0.68. And if I made a 2 there, what would it be? It'd be 0.95. No matter what the mean and the standard deviation were, you tell me what the mean and standard deviation are, I can figure out what this number is, I can figure out what that number is, and the probability would be 0.95. Right? Now, I'll warn you, it's not exactly 0.95. Remember, the empirical rule always uses the word approximate. It's approximately 0.95. Right? In a little bit, we can compute exactly what it is, at least out to 10 decimal places. But what if I now decide to hack you off and I do something like 1.5 sigmas instead of a nice integer multiple of sigma? Now how do I do it? Well, back to this drawing, where would 1.5 standard deviations put me? So what are these numbers that I'm asking about? Well, 1.5 times 12 is how much? 12 is our standard deviation. 1.5 times 12 is 18, right? 12 and then half of 12 again. So 18. So I got to go 72 plus 18. Where would that take me to? 90. So that's going to be about right there. Right? And if I go the other side, 72 minus 18 would take me to 54. So about right there. Okay? And what I'm asking for is the area of that region under the normal curve. It's a probability distribution function. Areas under it give the probability of being in that region. Well, I don't know how to compute this. But I can get a good guess as to what the value is going to be by looking at the empirical rule. If I had given you 60 to 84, we know the answer is 0.68. If I had given you 2 standard deviations, which would take me to, what would it be? 72 plus 24 would be 96. So 96 down to 48, then we know it would be 95%. So the area I shaded is somewhere between 0.68 and 0.95, right? Which one will it be closer to? Probably closer to the 0.95 than the 0.68. Well, I'm going halfway in between the two. The part that's left over gets skinnier and skinnier. So it's not halfway between the two numbers. Okay? But you'll see that in a second. Well, let me do some algebra on this thing just because algebra is fun. Ooh. When you have a three-part inequality like this, as long as you do the same thing to all three parts, you haven't changed it, right? So the first thing I'm going to do is I'm going to subtract mu from all three parts. And that's going to leave me with negative 1.5 sigma less than x minus mu less than 1.5 sigma. Right? Now I'm going to divide all three parts by sigma. Now remember with inequalities, if you divide or multiply by a negative, you got to worry about switching the direction of the inequality. But what about sigma? Is it a positive number or a negative number?
Yes. No.
Sigma is a standard deviation. Can standard deviation ever be negative?
No.
No. It's always a positive number, right? So I don't have to worry about flipping that. So I can just divide through everything by sigma. And the sigmas cancel here. And I'm left with that guy in the middle. Does that guy look familiar? If you subtract the mean, divide by the standard deviation, you just computed a z-score. Excellent. Z-score. So I can write this as negative 1.5 less than z less than 1.5. So this probability equals that probability. Now for us, using a TI-83 or an 84, we don't really have to go usually to z-scores to compute things. The book will teach you to compute probabilities under a normal distribution by using the table in the back of the book. There's a normal probability table in the back of the book. But obviously you can't have a table for every normal distribution there is. I got a normal distribution for pulses that has a mean of 72, standard deviation of 12. But then there's one for heights that's some other mean, some other standard deviation, and one for everything you can imagine. But they can always be converted into z-scores, and all z-scores would then follow the same normal distribution. What would the distribution of z-scores be? Z-scores have a normal distribution with mean equal, well, if you start with x and you subtract the mean off of every value of x, then the new mean is going to be the mean of x minus the mean of x, which is 0. So this thing's going to have mean 0. And the standard deviation, when I divide by the standard deviation, I've rescaled it down to a standard deviation of 1. So z-scores have a normal distribution with a mean of 0 and a standard deviation of 1. And that is called the standard normal distribution. Okay, so z-scores follow a standard normal distribution. Now, we do need to know about the standard normal distribution because there will be problems where you're asked, they won't even give you the mean and the standard deviation. They'll just say, in a particular distribution, what's the probability that you fall within 1.5 standard deviations of the mean? That's asking you this. Within 1.5 standard deviations of the mean. If it's a z-score, then that's from negative 1.5 to positive 1.5. So how are we going to compute that? Well, we aren't going to learn to use the table in the back of the book. That's the old-fashioned, obsolete way to do it. Since we made you spend $800 on these calculators, it's all built into there. Okay? So here's how it works. To compute this, I know that a z-score follows a standard normal distribution, and I know that the mean and the standard deviation of a standard normal are 0, 1. So click on, I'm going to clear my window, and then I'm going to click second function, vars. And that vars button is right here below the arrows. And above the word vars is in little letters you can't read, DISTR. Guess what that's short for? Distributions. So in that is a whole list of probability distributions that the calculator has built into it. Some of those we'll use, most of them we'll never get to. But the top one says normal PDF, the second one says normal CDF. Okay? Now, PDF sounds right, because what PDF stands for is probability distribution function. That sounds right, but it actually isn't right. What that function gives you is the height of the probability distribution at any point along the axis you ask it to. But I don't care about the height of it. What I care about is the area underneath it. Right? So that's cumulative distribution function, which is CDF. So we will use the normal CDF function. The normal PDF we will never use in this class. So you can just remove it from your calculator. Okay, you can't do that. So do like the guy in Apollo 13, the Apollo 13 movie. Did you see that movie? And when, I think it was Kevin Bacon, when he started to get kind of punch drunk from lack of oxygen or whatever it was, there was a button he wanted to make sure he didn't push. He put a little piece of tape over it and said, no. He taped it up there. Don't push this button, right? That's what I want you to do with normal PDF. Put a little piece of tape over it or something. Don't use that one. On the next exam, which is a week from today, somebody will do that. Don't let it be you. Right? Use normal CDF, not normal PDF. Right? So the normal CDF function works like this. You enter 4 arguments. An argument means a value that you put in that it needs to know that value. And those 4 things are the left bound of the region you want the probability for, the right bound, the mean, and the standard deviation. Okay? So let's do this one first. Move your cursor down to normal CDF, press enter, and it puts the normal CDF function there with a blinking cursor after an open parenthesis. And that's saying I need to know some information here. So it wants to know these 4 numbers. So what are my left and right edge here? Negative 1.5 and 1.5. Now one of the things that happens occasionally on these calculators is people will use the minus sign, like if they're going to do subtraction, they'll use that for the negative, and then it gives them a syntax error. You have to use the one that has a button that looks like that, right? And it's a white button down at the bottom. So negative 1.5, comma, 1.5, comma, 0, comma, 1. And you really don't have to close the parenthesis. It knows that there can only be 4 things, so it works okay if you don't do that. Okay? So that gives us a probability of 0.8663. Now, is that in the ballpark of what we thought it ought to be when we looked at the picture? we said it's going to be bigger than 0.68, but less than 0.95, but closer to the 0.95 side of it. Makes sense, right? Take the time to do that. When you work these problems, what I want you to do is I want you to draw a normal curve. I want you to label, knowing that, okay, halfway down the hill is 1 standard deviation, so where's my number go? Figure out where it goes, shade the region you want the area for, and then make a ballpark guess in your mind. Well, it ought to be a number around this. Then when you work the problem, you can look at that and go, well, that can't be right. If you're way off from what your ballpark eyeball says it ought to be, then you know I probably made a mistake. Okay? But if you're close, like this is close, say, yeah, I must have got that one right. I can go on to the next one and feel good about it. Okay? Now, the normal CDF allows us not to have to convert things to z-scores in our calculator. We can get the same exact thing by going directly with this picture. Looks like I've erased it, but this probability with mu minus 1.5 standard deviations, we said that was 54, didn't we? Is that right? And up to, what was the upper end? 90? Yeah, plus 18. Right? So we want to know the probability that x is in between those two numbers. So in your calculator, do second function vars again. Go down to normal CDF. This time, what's the area of my, well, I still had the drawing. I could have looked right there. The left edge is 54. The right edge is 90. But the mean and the standard deviation are different. What's the mean now? Instead of 0, 1, it's 72, comma, 12. Press enter. You should get exactly the same number that you got the other way. Okay? So you can do it either way. When you go to work the homework problems, if you get stuck and you click on help me solve this or show me an example, they're going to show you convert the 54 and the 90 to z-scores, go to the table in the back of the book, look it up, add the areas, and you got it, right? Don't do it that way. I wish there was a way to get it to do it with the TI-83, but there isn't. Just know that, well, if I get stuck on one of these, I'm using my normal CDF function in the calculator, and then you may just click on Ask My Instructor and say, what numbers do I put in here? I can't figure it out. Okay? So that's the normal CDF function. You can also ask or answer probability questions like this. What's the probability that x is greater than 100? What's the probability that a randomly selected person has a pulse that's greater than 100? Or an equivalent way to think of that is, what proportion of the population have pulses above 100? What'd you say? Little bitty. It's going to be a small percent? I agree. And that's the thinking I want you to do. I want you to get a ballpark estimate and think, well, it's got to be a really small probability, because that's a high pulse for a resting pulse. And where is 100? Well, if this is 72 and this is 90, 2 standard deviations we said was at 96. So that's about there. So 100 is clear out there. So what's the ballpark estimate there? Pretty near nothing. Yeah, I like that. If I had asked for 96, what would this area be? You can do that one in your head. What'd you say, Aaron? Somebody over there said something. Nobody's admitting it now. Well, if I had used 96, what proportion is within 2 standard deviations? 95. So how much is not within 2 standard deviations? 5%. And of that 5%, half's in the upper tail, half's in the lower tail. So if I had said 96, which is exactly 2 standard deviations, there'd be 2.5%, or 0.025. So our ballpark estimate is, well, it's going to be less than that, right? So it's going to be less than 0.025, possibly quite a bit less. Right? So we go to our calculator. Well, we have a problem now with left and right. The left is easy. The left is 100. What's the right edge of my shaded region? There isn't one. So we put in positive infinity. Now, calculator doesn't handle infinity too well, so just put in a big old number. Right? So what I always tell people, just put in a bunch of 9s. 9, 9, 9, 9, 9, 9, 9, 9. Okay? Which is great. The author says put in 1E99. But it always takes me a while to figure out where do I get the E. This is scientific notation. What this means is 1 times 10 to the exponent of 99. So 10 to the 99th is a 1 followed by 99 zeros.
Second comma.
That's a big old number. But yeah, it's a second function and comma, you get the E. So I'm going to go back to second function vars, get my normal CDF function. I'm going to enter my 100, comma, and then I'm just going to put in a bunch of 9s. Now, the number of 9s that you use, you have to be a little bit careful with. The 1E99 will always work. That number is huge. But the idea is you got to go out a lot of standard deviations. You're just telling the calculator, I'm going way out there. Okay? If I'm doing pulses, then even 3 9s is plenty, because a pulse of 1,000, that's pretty far out there, right? But if I'm doing like home prices, the mean home price might be 150,000, so I need a lot of 9s to be way out there in that distribution. So just use a little bit of common sense on the number of 9s, and generally if you just hit a bunch of them, you'll be fine. So I put in, looks like I put in 6 9s, that ought to be plenty. Put a comma, and then the mean is 72, standard deviation of 12. So there is the probability, 0.0098. And that matches our ballpark estimate. We say, well, that'll be a number less than 0.025, and that number is roughly 0.01. So only about 1% of the population has a resting pulse that's 100 or bigger. Okay? What happens if I ask, well, let's just do this. What's the probability that x is less than 100? Now I'm shading on the other side of 100. So I'm shading over here all the way down to negative infinity. So what's my left edge this time? Negative 9999999. Or negative 1E99. Okay? Now, usually at this point someone says, well, wait a minute, this is pulse. Pulse can't be negative. Can I stop at 0? And in this case, yeah, if you stop at 0, you're going to get the same answer to at least 4 decimal places. But theoretically, a normal distribution never stops. So we just make it so we don't have to think about it. Go negative infinity or positive infinity. So has anybody got this done? 0.9902. Right? So you put in negative 9999999, right edge 100, mean of 72, standard deviation of 12, and you get that number. Now what do you notice about these two numbers? They add to 1. So I could have done this by just saying, well, it's 1 minus that, because these are complementary events, right? The complement of being bigger than 100 is being less than 100. So I could have done it that way, but okay, let's see. There's one more topic that we have to get through, and then hopefully I'll have enough time left to work some of the homework problem, the practice problems that are similar to the ones on your online homework. If not, then I may have to end up sending those out by email. Because even though we get through this in class, when you start doing it on your own on the homework, it's going to be a little confusing at first. But suppose instead of asking the probability for a given range, I give you a probability and I ask what value of x has that probability. So in other words, maybe I say, what value of x let me write it as a sentence, and then I'll make it probably understand. What pulse has 90% of the population below it? That's a kind of a homework problem that you might get. What pulse has 90% of the population below it? Well, I know if I go 2 standard deviations, I have 97.5% of the population below it. Because a minute ago we said, well, 2.5% would be above it, so 97.5 would be below it. So where's my ballpark idea of this answer? 90%. Is it going to be bigger than 96 or smaller than 96? Smaller than 96. But is it going to be clear down to 84? What percent is below 84? 68 down to here, and then another 16, and that's 84. So it's just coincidence that 84 has 84% below it. But it would be 84%. Well, I want 90%, so I need to be a little bit on that side of 84, but not all the way to 96. So I know that my x I'm looking for is somewhere in there, right? I just don't know exactly what pulse will do it for me. So I want this area to be 0.90. So this time, they didn't give me the number in my probability statement, they gave me the answer to it. That's an inverse function to the one we just used. Remember what an inverse function is from algebra? An inverse function undoes what the other function does. So if the normal CDF function gives us a probability back when I plug in a value, then the inverse to the normal function will give me a value back when I plug in probability. So go back to your second var, your distribution, and the inverse norm function, the third one down. Inverse norm, and the inverse norm function needs 3 arguments. So it's inverse norm. First one is the percentile. Then followed by the mean, followed by the standard deviation. Now, what do we mean by percentile? Well, in other words, the inverse norm function is going to return for us the 90th percentile. And that's what this question says. Another way I could have worded this is, what is the 90th percentile pulse? That means the same thing. So the percentile that you want goes in there. So in this case, that's 0.90. And the mean is 72. The standard deviation is 12. So put that into your calculator in your inverse norm. And you get 87.379. Now, keeping 3 decimal places of accuracy is really uncalled for here. This is pulse, heart rate. You know, you don't give your pulse to the 1000th place, right? But, you know, just keep whatever they tell you to keep on the online homework. A 10th would be plenty, but even going to integers would be fine. Does that match where we thought it ought to be? Yeah. Right? this percentile is the probability or area from negative infinity up to x, where x is the number you're trying to solve for. So I want to stress that it's from negative infinity all the way up to x. It's on the left side of x. So I'll put that in parentheses, left of x. So, keeping that in mind, what value of x as 15% of population above it? See if you can figure out how to work that one. And I threw in an extra little wrinkle. Okay, I have a candidate answer, 15.56, right? Let me ask you, Eddie, with that ballpark estimate, does that make sense?
Because we got,
So a pulse of 15 has 15% of the population above it, which means 85% of the population has a pulse less than 15?
less than,
Oh, that doesn't make sense.
15%.
So always think about your answer. Does that make sense? Am I looking for a number? Am I looking for a proportion or probability, or am I looking for a pulse?
Then it's 84.
What does it say? What value of x? What is x? That's a pulse. So my answer needs to be a pulse, and it needs to be a pulse that sounds right.
How about 84.4?
That sounds a lot better, 84 something, right?
When you said above it, it threw me off, and then I subtracted the answer I got from 100.
Ah,
I gave it 50.
yeah. So what do you have to do first? If I want 15% above the x,
0.85.
I got to tell the calculator what area is below the x, because I need the area from negative infinity up to that x. And that area is going to be what? 0.85. So 0.85 goes in there. And I'm going to write below it 1 minus 0.15. And then it's 72 and 12 again. And what did you say you got?
84.44.
84.44. And it makes sense that it ought to be a number that closely hugs this one, right? But is a little bit bigger. And ballpark, empirical rule tells me if it was 84, what percent would be above there? Can't do these in your head too fast yet, but you'll get there. 68% is in the middle, so 32% is not. Half of that 32 is up there, and that's 16%. So 16% is above 84, so I want 15%. I have a number that's pretty close to 84, but a little bit bigger, and that number makes perfect sense, right? 15 does not make sense. So always look at your answer, see if it makes sense. You'll catch an awful lot of mistakes that way. I guarantee you on the test, if you write 15 down, but take the time to go, well, wait a minute, you'll catch that mistake and you'll be fine. Right? If you don't take the time, you just, oh, I'm in a hurry, I put down an answer, let me go to the next one, then, minus 6 points or whatever it is. Okay? So that's the inverse norm function. The inverse norm function gives us percentiles. But sometimes they don't ask in a percentile way. You've got to convert it to a percentile way, then get the x you want. sometimes they do real complicated stuff. Find the value, find how many standard deviations contain the middle 50%. Right? How many standard deviations contain the middle 50% of a normal distribution? And they don't even give us a mean and a standard deviation. How in the heck am I going to work a problem like that? Well, I'm going to draw a normal curve. I want the middle 50%. So that's in there. And I know it's less than one standard deviation on each side, because one standard deviation would take me to 68. So I want this area to be 50%. Right? Now, if they're talking about number of standard deviations, what should I be thinking? Z-scores. So I know my distribution is standard normal. It's 0, 1. Right? So then I can say, well, let me find this value of x right there. What area is below there? 0.25. Now I know the area to the left for my inverse norm. I know the mean is 0, the standard deviation is 1, and I got my x. You should get a negative number back. That same number, so this will be negative x, this will be x. By symmetry, you know what the upper one is going to be.
What would your first number be? Would that be the 50 or the 0.25?
This is the 0.25. Because you always have to go area to the left. If I had shot for this x, my area to the left would be this 50% plus this 0.25, I'd have 0.75. And then this is going to be 0, and this is going to be 1. Okay? Now, does anybody do that one? Did you get a number? Nobody did it?
I want to
Okay. All right, well, I'm out of time, so if you need to get running, go ahead and go, but I'm going to go ahead and get a number there. Did you get it?
negative 0.67.
Negative 0.67.
What do you put for the last one?
A 1, because this is standard normal. Number of standard deviations is standard normal, which has mean 0, standard deviation of 1. Okay. I think my projector is kind of clouding things here. There. Does that look better?
So the exams are Friday, not Monday.
What's that?
You know, the exam.
The exam will be next Wednesday, not Monday. Yeah, today's Wednesday. The exam will be a week from today. Okay, did you shut that off?